Swayam Prabha. Digital India. Educated India.
Okay, so good morning all of you. So in the last class we were looking at the derivation of continuity and the momentum equations, and we started off with the derivation of the energy equation in a Cartesian coordinate framework, and today we will continue and complete this derivation. So as we had seen, we have taken a cubic or a Cartesian coordinate control volume, and the contributions to energy, if you look at, so you have primarily the efflux of internal energy as well as the kinetic energy, which is crossing the control volume boundaries in all the three directions. I am just representing here on only two directions. You can also extrapolate that to the third direction. Apart from that, you have the efflux of heat by conduction. Okay, so that is this Q double prime. So you have heat conduction, which is essentially transferring the heat by diffusion process, and you have energy transfer by means of efflux of the internal and the kinetic energies, and also you have work transfer. So all the three are simultaneously, these are effluxes or fluxes of contributions of internal kinetic energies, the work, and the heat, which is all acting on the control volume boundaries. And as far as the change within the control volume is concerned, so we know that we can express the rate of change of energy in the control volume to the net efflux of energy across the control volume boundaries. Okay, and now we are also looking at, when we are looking at the work, we include the body force terms which are acting on the entire volume into the work terms. Okay, so they are the potential energy terms which we are adding as work. So if you look at the rate of change of energy, essentially, so this is the energy per unit mass. Okay, internal energy per unit mass is this U, capital U or small u, which you want to use. If I use small u, that conflicts with my velocity, therefore I am using capital U, and this is your kinetic energy per unit mass. So multiplied by the mass, which is your density times the volume. So this gives me the energy of the system, and therefore the rate of change of energy will be d of this divided by dt. Okay, so therefore if you look at on the right hand side, which is the net efflux of energy, we have to balance the energy which is coming in from the left boundary minus the one which is leaving, and similarly in the y direction and the z directions. And if you can do that and expand by Taylor series, if you calculate the energy rate of change of rate of energy in minus rate of energy out, so you end up with these three terms which we have written down last time. So similarly we can also express the flux of heat as well as the work. You know, the flux of work is a little bit more complicated, which will lead to additional terms which are coming in, but we can also try to expand and see how those terms look. So let us write down the net efflux of heat. Okay, so do you think that this is correct? Efflux of kinetic, and something is missing here, sign minus, there should be a minus here, right? So that is your flux of kinetic and potential energies coming in minus the one that is leaving, so this should be a minus sign here, right? And when we write the net efflux of heat, okay, so let us write it down. Can you say probably how it should look? Minus of dqx dx plus dq double prime dy plus dqz double prime by dz. So these are your fluxes into the volume finally. So anyway you have for each of these derivatives you have delta x and multiplied by the area, so everything comes out as a volume. You have delta x, delta y, delta z. Okay, so we can now introduce the Fourier's law of heat conduction. Okay, so you know that your q vector is equal to minus k delta t, right? So that can be introduced, and can you say how this can be written? So we can, the minus sign can be cancelled off. You can write this as d by dx. Strictly speaking, the thermal conductivity could be anisotropic. That means you can have different thermal conductivities in the different directions. So you can keep it within the partial derivative. If you assume that is isotropic and constant property, so this can be taken outside the partial derivative. Okay, so I am assuming here that thermal conductivity is isotropic, but could be a function of position, okay, because of its dependence on temperature. So I can express this okay. So much so for the net efflux of heat. So it's looking very straightforward. Now let us move on to the net efflux of work. Now this is a very lengthy expression because you have to consider all the terms which contribute to work. Okay, so if you do the same analogy and apply that to work, so how does the work terms appear? Can you think about, so you are writing the net efflux of internal and kinetic energy is heat, and in the analogous way, so what are all the terms which contribute to work? The forces, okay, all the forces, the surface forces, the volumetric forces, they are all included under the work term. Okay, so if you go back and revisit your momentum equation, so you look at what are all the surface forces and body forces acting, and then you multiply them with the respective velocities. Okay, so that will give you the amount of work. Okay, so that is basically the rate of work, right? The force into displacement divided by time, so that is the rate of work. So all these are in rate terms, alright. So if you do that, so the net efflux of work in all the three directions, so I am just going to write down, and you just please verify if they are correct. And also the sign convention is that, so I am assuming the forces which are all acting, the net forces acting in the positive direction are all positive work. Okay, they contribute to the positive along a positive x direction. So this should be looking like this, d by dx from the x momentum equation. You have d sigma xx by dx, so I am just multiplying by the corresponding velocities in that particular direction. So u sigma xx, right? You can verify that from your momentum equation expression. Okay, u tau yx. So these are the stresses, the normal stresses, normal viscous stresses and the tangential stresses which are acting along the x direction, multiplied by the corresponding velocity in that direction. Alright, so this is the contribution, this is the net contribution to the efflux of work. So we have w into tau zx. Okay, so this is in the x direction. Okay, so this should be u here, right here. So you have to sum them in all the directions. Okay, so you can say plus, you can just write that in the y direction as well. You have v. Can you tell me what this term should be? Sigma yy plus d by dx into v into tau, is it yx, xy? Okay, so you look at this, the last subscript here denotes to the direction that we are talking about, in which you are calculating the work or momentum. Okay, plus your d by dz of v into tau Z, Z, Y. Okay, so this is a good exercise for you. Plus you have d by dz of W into sigma ZZ plus d by dx of W into sigma, what should be this term, tau xz plus d by dy of W tau yz. Okay, so these are the contributions to the surface forces. So what should be added to this? What are the other contributions to work? Body forces. Okay, so that also we can, yeah, so that is coming under the body forces. Okay, so that is the potential energy contribution that is added under the work. So this will be rho u. So I am taking rho common because rho is common in all the three directions. You have u gx vgy plus w vgz. Okay, now this entire expression right here I have to multiply by the volume, and same with respect to this, because this is a volumetric force, you can see directly this is multiplied by the volume. The other ones you know from the Taylor series expansion, we have this delta x delta y. So any questions on this? I hope you have identified the different contributions to the flux terms, as well as you know rate of change of energy within the control volume is straightforward. So now we will just balance that using the principle of conservation of energy, and we will write down. So this will lead to a big expression here which can be written as d by dt. Okay, let me number this as let me call this as number 1 here. Okay, so from 1, so I am going to substitute for all these terms into 1. So this is d by dt of rho capital U plus the kinetic energy so this is the rate of change of energy within the control volume, plus you have the terms which are, so actually strictly speaking what we could have done, we can combine the rate of change of energy and the flux terms together into a total derivative. So I am just going to first write it down and then combine the convective terms and the rate of change terms into one single total derivative for a compact notation. So right now I will just write it in the full form. So this is d by dx rho u. Probably I have missed the rho here. Okay, so this should be a rho here, right? Okay, because this is the flux. Okay, so that should be mass flux multiplied by the area, which will give you the flow rate of this particular quantity. All right, so you can write this in terms of rho u. So u plus u square plus v square plus w square by 2. Okay, plus you have d by dy rho v So I have taken all the efflux of kinetic and internal energies towards the left hand side and combined that with the rate of change of energy. So this is my left hand side terms. Now this should be equal to, I am not going to write down, it is taking too much of space here. I will just mention this is equal to net efflux of heat, right? So you can just write those terms here, net efflux of heat plus what? Net efflux of work. Okay. So now on the left hand side term I can just say from the LHS, so the term right here, the time derivative and the spatial derivatives can be combined into one total derivative. If you also observe, we can also simplify this a little bit. We can say take u plus u square plus v square plus w square by 2 common, so this will be d by dt of rho plus d by dx of rho u plus this plus this. So what is that? That is a continuity equation, okay, which will be automatically satisfied, so that will go to 0, and therefore you can say that you can take rho out and we can write this as d by dt of this plus d by dx of u into this plus d by dy of u into this, okay. So that can be written as rho into the total derivative of d by dt with respect to u plus right, because the continuity is satisfied, so I can take the rho out, okay. So I am not making any assumption here, I am not making any incompressible assumption, but you can see that if you expand this, the compressible form of continuity itself is satisfied. So I can write this as rho into the total derivative of the internal and kinetic energies. So the LHS is simplified, so now I can equate that to the other terms. Okay, so that will be equal to my d by dx of k dt by dx plus d by dy plus I have the work terms So what I am going to do here, I am just clubbing these terms, d by dx terms here in the from the x momentum, the y momentum and the z momentum together, okay. So I am taking d by dx common and writing all the terms inside that, so that should give me u sigma xx plus v tau xy plus w tau xz. Please check if these terms are right, plus d by dy of u tau yx plus v sigma yy yz zx plus v tau zy sigma zz plus I have the body force terms rho into ugx plus vgy w vz. Okay, so this is my complicated form of the energy equation. Now what I am more interested finally is the I should write down an equation for the change in internal energy of the system more than the total energy, which includes internal energy plus the kinetic energy. So I want to somehow eliminate the kinetic energy part and write down an equation governing only the internal energy, which is the direct indicator of the temperature, change of temperature of that particular system. So how can I do that? How can I eliminate the mechanical energy component from this? Can we use the momentum equation somehow, and we can construct an equation for mechanical energy from the momentum equation. You know the momentum equation is written for u, v and w, okay. We can multiply those with u, v and w in each of these directions. We can sum them up together and you will get this particular form on the left hand side that can be subtracted from here, and this component can be eliminated straight away, right. So if you go back and see how your momentum equations are written, okay. Now this is the, let me call this as equation number 1. I already have one, so I will call this as number 2, okay. So how are we going to do it? If you look at the momentum equations on the left hand side term, how do we have the total derivative? Can you go back and check? d by dt of du by dt, for example in the x momentum, right? Okay, so this is the left hand side term, correct? So if we multiply this by u, okay, so this will be u du by dt, which can be written as du square by 2, correct? This is nothing but u du by dt. So the same thing we are going to do in all the three directions, multiply by the respective velocities and sum them up. So what you will get, plus v square plus w square by 2. So now you see the left hand side term of the energy equation, so this and this are common, right? So if you subtract this directly, you will eliminate kinetic energy, so you will retain only the internal energy component. So now we also have something on the right hand side. Of course, when we subtract, we have to subtract both sides. On the right hand side terms, what you will get, can you just go back to your momentum equation and multiply and tell me? So you have u into d sigma xx by dx plus d tau yx by dy plus d tau zx by dz. So this is the x momentum which you are multiplying by u, plus what, a y momentum v into d tau xy by dx plus d sigma yy. So what should be this term, third term, d tau, in which direction it is, y direction, and the derivative z, plus you have d tau x z plus d tau yz plus d sigma zz by dz, okay, plus if you multiply your body force terms also, you have rho into ugx vgy plus, okay. So this equation is called the mechanical energy equation. Okay, so this is nothing but something like conservation of mechanical energy from the momentum equation. Okay, so if you write your momentum equation, automatically that satisfies this. Okay, but you are explicitly now writing another equation for conservation of mechanical energy. So let us call this as number 3. So now if you subtract 3 from 2, that means you are trying to eliminate the kinetic energy term and only retaining the internal energy. So that's going to get us where we want to go in terms of calculating the temperature of a system. So far, although you are more familiar with an energy equation involving the temperature, we have not introduced, strictly speaking, an equation for temperature. Although that appears on the right hand side term here, on the left hand side term still you do not have something for the temperature. So we are slowly going there, okay. So subtracting 3 from 2, on the left hand side term you have rho du by dt, okay. So this is your change of internal rate of change of your internal energy of the system. On the right hand side terms, you retain your efflux of conduction, efflux of heat by conduction. So this term comes as it is, d by dx and now coming to the other terms, if you look at typically this term here and there, so you can eliminate, so you can expand this as your d by dx sigma xx du by dx plus u into d sigma xx by dx, so that cancels. So what should be the remaining terms after you cancel off you have sigma xx du by dx, right, plus tau ix into du by dy. Okay. So what I am going to do, I am going to combine the like terms together. So I am going to combine the normal stress terms together first. So you will be getting dv by dy. Okay. So I am looking at this particular term here, here, and writing them together, plus I have sigma zz dw by dz. Now the other tangential stresses I am combining them. I am also using the fact that tau ix is equal to tau xy, okay, and tau iz is equal to tau zy and tau xz is equal to tau zx. So if I use that, I can combine tau ix and tau xy terms together, and that will be dv by dx plus du by dy, because if you look at tau xy here, so this will be dv by dx, okay, and this will be du by dy. Okay. So these two terms can be combined together, and tau xy is equal to tau yx. Similarly, the tau yz, so dw by dy plus dv by dz plus tau xz, what should be the derivative inside? Du by dz plus dw by dx. Okay. So therefore you have another nice equation which is still not simplified completely, but this is an equation for the conservation of the internal energy of that system. Alright. So now what we are going to do, so how do we simplify this further? How have I written? Okay, so this is coming from the momentum equations. You know the x, y, z momentum equations, right? So I am multiplying each of those momentum equations by the respective velocities and summing them together. Okay, so for example, on the x momentum you have u du by dt, so I can write that as d by dt of u square by 2, correct? And similarly in the other direction I sum them, and also the right hand side I am doing that summation. So this is okay. So now how do we further go ahead, and let me write this as equation number 4. Still you have some unknowns on the right hand side, right? You have terms related to your stresses which have to be closed. Huh? Now how do we close those terms? Stokes hypothesis, yes. So we have to first derive we have to use some relationship between the stress and the strain rate. So Newtonian fluid approximation first, and of course Stokes hypothesis. Now also if you do that, you will derive that for a compressible fluid, but we are more interested in incompressible fluids in this course, so I am directly going to substitute the Newtonian fluid approximation for incompressible fluid now directly, okay, because otherwise we will accumulate more and more terms. So for incompressible fluid or for incompressible flows, so incompressible flows, so what I am going to do is, can you tell me, for example, sigma xx should become minus p, so this is your pressure force plus okay, after the Stokes approximation, so minus 2 by 3 mu into divergence of u. Now for incompressible flows that is going to be 0, right? So that term can be neglected. So what is the other term? Plus 2 nu du dx, right? So that's why I am going to bring in that approximation, that divergence of u is can be eliminated straight away. So one term is actually simplified. So I can write this in the other directions. So now my tau xy and tau ix is going to be the same for compressible or incompressible fluid, okay. So that is nu into dV by dx plus du by dy. So and also you can do that for tau yz is equal to tau zy. Please you can fill in. Okay, now you can substitute this into 4 and we can write down in terms of velocities. Okay, so what I am going to do, just only this term right here, which I can probably highlight. So this highlighted term alone I am just going to express in terms of velocities. So my sigma xx du by dx plus sigma yy dv by dy plus sigma zz dw by dz. So if I substitute this, so I am going to, you can see directly I can take p common, du by dx plus dv by dy plus dw by dz. So satisfies incompressible continuity. Okay, so if I substitute for this, okay, so that term I am going to eliminate, and you will have 2 nu into du by dx into du by dx plus 2 nu into the same thing. So finally you will have 2 nu du by dx the whole square dv by okay. So the incompressible approximation is going to simplify this particular the normal stress work, okay, so to a great manner. So therefore if you look at this terms here tau xy, you can see that is already nu dv by dx plus du by dy. So this and this multiplies and this will be again whole square, okay. So these are relatively straightforward terms. So if I combine that, I can once again express equation 4 as rho du by dt should be plus 2 nu, and I have this term right here du by dx the whole square okay, plus I can take 2 nu common for these terms also. I can take 1 by half factor out, so that this is 2 and 2 cancels and it is nu. And what should be the other terms? If you substitute for tau xy into whole square of each of these, right? So dv by dx plus du by dy the whole square plus half of my dw by dy plus dv by dz the whole square plus half of du by dz plus dw by dx the whole square, okay. So this is my equation number 5, and now it looks more familiar to you. I am going to group this set of terms contributed due to the work as one single term, which is denoted by the symbol right here, and this is called as the viscous dissipation. See all the surface forces, you can see the body force terms get cancelled off. Finally the body force terms do not affect the energy in any way, alright. So only the viscous forces are playing the role, the surface forces, and they are all grouped together as what is called as a viscous dissipation contribution to the energy internal energy of the system. Okay. Now some people make an approximation that under certain criteria and conditions this is going to be negligible, and therefore you can see the familiar form of the energy equation. Okay. So we will make a few approximations now and simplify this equation for couple of conditions. So the first thing, if you introduce the fact for that your du, that is your change of internal energy, is related to your temperature. Okay. So if you say that it is Cv dt, and for an incompressible fluid it does not matter which specific heat you use, whether it is specific heat capacity at constant pressure or constant volume, they are the same. Okay. So for incompressible fluid, okay, so your du is the same as the change in enthalpy, therefore your Cv is equal to approximately Cp. Okay. So this is just one constant specific heat I can use for incompressible fluids, and therefore I can express that in terms of temperature. So I can write this as rho C dt by, which is equal to C. Okay. So on the right hand side I have this term, conduction terms, plus I have the viscous dissipation term. So this is the familiar form of energy equation for incompressible flows. Okay. Now we can also make some more further approximations to this.
So how that half term comes in the equation by half dv by
Okay,
dx?
so because this 2 and 2 should cancel off, the term is actually nu into,
Mu would be there.
this mu is common to all of these. In fact I should put another big bracket here. Yeah, you are right. Yeah, so 2 nu is common to all these terms. Huh? No, I am calling this entire thing as phi. Okay, this is a single term which is the viscous dissipation term. Alright. So for steady flows, first approximation, I am going to reduce this incompressible energy equation for steady flow under constant property assumption that my thermal conductivity is invariant of position with constant or uniform property everywhere. So this is going to be, the time derivative is going to disappear. You can write this as u dt by dx plus v dt by dy plus w dt by dz, that is equal to k by rho Cp, which is nothing but the thermal diffusivity, okay, alpha. So I can write my k by rho C as alpha d square t by dx square plus d square t by dy square plus d square t by dz square plus phi by rho C. Okay. So for 2-dimensional flows I can make a further approximation that the third dimension is not important. Plus phi by rho C, where phi becomes even more simplified. Okay, for 2D flows I can expand my so that will be only 2 nu into du by dx the whole square dv by dy plus half of dv by dx plus du by dy the whole square. Alright. So finally when we are working with the energy equation in this course for doing the analytical solutions, we will be looking at these approximations, okay, incompressible flow and mostly in 2-dimensional. We are concerned only with 2D flows for analytical solution. So this is the form that we are going to work, and you can see the viscous dissipation also gets substantially simplified. Okay, in a coordinate free representation you can also do this, and you can suppose you neglect your viscous dissipation terms in a coordinate free representation, neglecting phi. How can you write this? Okay, so suppose you don't make a steady state approximation, but still it's an unsteady, you can write this as dt by dt plus del dot u vector times the temperature, which is equal to alpha del square T. So this is my equation for temperature, right? So this is your advection term, this is your diffusion term right here. So they are represented in terms of your divergence and your Laplacian, which you can substitute for the corresponding coordinate system. Okay, so this is a common representation. You can, if you want to write this in cylindrical or spherical, you please substitute in that particular coordinate system the corresponding divergence operator and the Laplacian operator. We will come back to that. Okay, so right now I am just concerned only with the derivation. We will non-dimensionalize these equations, then only we can find the criteria where we can neglect those terms. Otherwise, when everything is dimensional, we cannot find out exactly, you know, when this is important and when this is not. When you non-dimensionalize, you find in terms of non-dimensional numbers. Okay, there is a particular number associated with it that is called the Eckert number. If the ratio of Eckert number to the Reynolds number is very high, the terms become important, viscous dissipation. Otherwise, you can neglect. Okay, so usually for even in the incompressible flows, if the flow velocity is high, or if you are going to the other limit where you are looking at extremely slow flows, that is creeping flows, under that is called Stokes approximation. So under these two categories, that term becomes very important. For most of the intermediate velocities and intermediate Reynolds numbers, so that term can be safely neglected. Okay, so very quickly in the remaining time, I am going to introduce to an alternate way of deriving these equations. So far what we have done is taken a control volume which is probably in a particular aligned to a particular coordinate system, and we have derived it nicely. So what if you want to apply this to an arbitrary control volume of any shape, and if you want to reach to this particular form, which is a coordinate free representation. Okay, so the way to do that is by what is called the Reynolds transport theorem. So I will give you some brief introduction into the Reynolds transport theorem now, and probably in the next class we can quickly do only the energy equation derivation from the Reynolds transport. The momentum equation, I think you can try it out yourself. So any questions so far on this? Okay, I think some of this is already familiar to you. Okay, so this is through Reynolds transport. How many of you are familiar with the Reynolds transport theorem? One, only one. I think whoever has taken the incompressible flows, probably this was introduced to you, right? Okay, so I mean, if you look at the undergraduate level, usually we do the derivation in the Cartesian coordinate system. That is the easier one to visualize, whereas most of the graduate fluid mechanics, the governing equations are directly started on a coordinate free control volume. So let us take some kind of an arbitrary shaped control volume. So let us say the volume of this, total volume of this at a particular instant of time is V. Okay, and let us say there is a differential volume delta V. Okay, there is a surface normal which is pointing outward, and there is a velocity which is also oriented in some particular direction. Okay, so this control volume is actually moving. Okay, and if you take a differential amount of volume, you draw the surface normal and you see the velocity is pointing in some direction. Okay, now the surface of this is S is given some value S at this time t. Now after some time you will find that this volume is changing after a period of time. So if you go from t to t plus delta t, this volume deforms into some shape like this. Okay, so not only the shape but also the volume is different. So I am going to write this as t plus delta t, the corresponding volume, and also your corresponding differential volume also changes, right. So if you overlap these two volumes, so this is the volume at t plus delta t and this is your previous volume, say. So this differential volume right here has changed from t to t plus delta t, and if I look at only this particular differential volume and I draw the full view representation of that, so it is going to look something like this. Okay, so this is my differential surface delta S, alright, corresponding to this volume. So I am just drawing a 3D representation of this particular segment alone. Okay, now you know that this has a velocity vector like this and this has a normal like this. Okay, so if you align the velocity vector in the direction of the normal, so this distance between these two volumes, that is the displacement from this position to this position, how can you calculate? That gives you the amount that it has actually displaced from this time to t plus delta t, velocity into time. So my velocity in the direction of normal will be u dot n into delta t. Okay, so my total deformation of this delta v is actually going to be u dot n dt into ds. Okay, this is going to be the total deformation of this differential volume, correct. Okay, so this is the basics of this. So from here maybe I will take a couple of minutes, 2 or 3 minutes, and then go few more steps. So I can say if I want to define any property alpha, okay, so this is the property per unit volume, and now the volume is changing but this is a control mass, so that means the mass is constant but the volume is deforming. So therefore I have to define a property per unit volume, so that this alpha is going to be the same here or here. Okay, it's per unit volume property, and if I want to see how this property is evolving over time, okay, so I can write that I can calculate the change of this particular property over the entire volume. I can multiply this by the volume, so that is alpha into dv, and integrate this over the entire volume. Okay, so this is property per unit volume. So for a differential volume I multiply by that, I integrate it over the entire volume, this will give me the property for that particular control volume. Okay, so I want to see how this property is changing with respect to time, so I take the total derivative of this. Okay, so this is the rate of change of property over this control volume V, alright. So this I can express as limit my delta t going to 0, I can write this as 1 over delta t into the property at time t plus delta t minus, so this is at volume t plus delta t minus the integral of this specific property at t, right. So this is corresponding to volume t. So if I take this difference from the property at t plus delta t for this volume minus the property at t for this volume, so this difference divided by delta t is going to give me what is the change of this property, okay, due to the change in the volume and over time. Okay, so this property therefore is only a function of time. Okay, this is not a function of the volume because it's already a property per unit volume, so it is only a function of the time. So this is the starting point for the Reynolds transport theorem. So we will stop here and we will let us call this as equation number 1. So this is basically to express the change in the property with respect to time in terms of the final and the initial states. Okay, we will start from here and derive the transport theorem tomorrow.